welcome back to the Heidelberg Showing Colloquiums that we started off last week with Brian Smith, and today we have the first time our colloquium up here. We're very excited, and thanks for making it up on such a beautiful sunny day. There was coffee. Next time we might even manage to make cookies, you know, we'll do our best. But we have the series starting up again up here every time, and the bus schedule changed, so everybody's aware of that. And so today we have Kochanek, professor and Ohio Emerald Scholar. So if you look for it, it's an Emerald Scholar as well. And he told me before he was an M&M Scholar at one point, but then they changed it to Emerald. So he usually does cosmology and gravitational lenses, and of course we all know him very well from the LBT work that he's doing. He got his PhD in 1989 at Caltech, and there's way too many stations for me to mention and be brief in the introduction. So if you want anything else, just ask him yourself. But he will talk to us about dusty explosions from dusty stars today.
Thank you for inviting me. If I start to shake, scream, and run from the room yelling, it's just a combat flashback to the LBT board meeting that was here in October. You weren't there, Thomas. So I talk about a project that actually sort of started with the LBT. In the end, it turns out that the LBT became somewhat useless because the objects vanished from view in the optical and the near infrared. And the objects we're ultimately going to talk about are actually creatures of the mid-infrared, where we ended up mostly focusing on results from Spitzer. But it is sort of interesting is sort of where it started with an early image with the LBC cameras sitting up here on foci. And this is work done mainly with a series of people at Ohio State, John Beacom, Rubab Khan, who's a graduate student, Jose Prieto, who's a Hubble, Princeton, Carnegie Fellow, Chris Selgren, Chris Kochanek, Dorota Sejial, who's now working with Hubble, and Todd Thompson, who's a professor at Ohio State. So here's the general plan. We're first going to find a curious little population of things which some people relate to the star Eta Carinae in our galaxy. And there's a set of objects called supernova imposters. And the reason is fairly self-explanatory, is they pop up and people say, gee, that looks like a supernova. And then they turn around a few minutes later and say, oh no, it's not, it's an imposter. And so we'll talk a little bit about what those are. We'll talk a little bit about the dust physics that might be associated with these objects. Mainly just what happens when you eject material from a star and it forms dust and what you might expect to see from that. Then we'll talk about what some of these imposters are, and just to keep things crazy, I'm going to end up dividing the imposters into three separate groups. And so I'm going to talk a little bit about what I'll call classical imposters, which are actually massive stars behaving badly somehow. Then I want to talk about the ones which we ended up identifying as a side effect of these LBT observations, which are some new class of dusty transients that seem to be associated with the most massive AGB stars, but much less massive than these high-mass classical imposters. In many people's minds, these imposters are related to the great eruption of Eta Carinae in the 1800s. And in fact, hope to sort of convince you by the end of this that in fact these imposters actually have no analogy to Eta Carinae whatsoever. And so I'm going to spend a little bit of time on whether in fact we know of any analogs of the great eruption of Eta Carinae in the local universe. And then a little bit on what we can do in the future. So this term, the imposters, was coined by the Berkeley group of Skylar Van Dyke and Alex Filipenko in 2000. And essentially what defines them is they're a class of transients which at peak are substantially less luminous than a normal type 2 supernova. Typically a factor of 10 less luminous than a typical type 2 supernova. There's no hard boundary here. You know, if I go to a theorist, hand him a star, say, please blow up my star, you know, they're utter failures. Theorists can't blow up stars to save their lives. If we were to believe theorists, there are no supernovae in the universe. Okay? The stars, when they do manage to blow them up, actually have 10 times less energy than the supernova we do observe. So that actually the transients we're talking about here have the energy of theoretical exploding stars. Okay. Spectroscopically, they're characterized by what are called type 2N spectra. So type 2 means they show hydrogen. The N means that rather than the characteristic broad emission lines you would see in a regular type 2 supernova, they have quite narrow lines which are narrow as sort of 1,000 kilometers per second rather than 5, 6, 7, 8, 9, 10,000 kilometers per second. And so that's the end designation. And as I said, is the picture many people have in their minds is these are some sort of non-destructive eruption on massive stars. And what frequently is in the back of people's minds is this great eruption of Eta Carinae. Now, you're saying, okay, here's this guy, he's come into some obscure class of bizarre transients, and he's going to say, I want to waste an hour of my time listening to something about this obscure class of transients. So I'll give you some reason to pay attention. So there are two reasons. First of all is, you have a class which is defined, but frankly nothing is known about these things. Right? We don't know anything really about their rates very much, other than they're kind of supernova-like. We don't really know anything about their energetics. Okay? We know the energetics that's in the optical outburst. But, the optical outburst of a supernova tells you almost nothing about the energetics of a supernova. Right? Supernovae are absolutely horrible at actually radiating any photons. All of the energy is somewhere else. We don't really know the mechanism. Okay? There are words about the mechanism. It's believed to be radiatively driven rather than explosively driven. So the usual picture is a massive star like Eta Carinae is not wildly far from the Eddington limit. And so perhaps by playing games with opacities in the atmosphere, you can temporarily drive it into a phase where it has a very high mass loss rate. These theories are all at this level. Okay. They have an interesting rate. Right? They happen to many massive stars. If their rate is something like 10 to 100% of the supernova rate, it's not entirely clear because the completeness for these low mass transients, low luminosity transients in supernova surveys is unclear. They happen to many massive stars if they're happening at 10 to 100% of the supernova rate. So many massive stars must undergo this. And the most interesting thing is that if you go into the galaxy, you don't really see the transients, except for Eta Carinae. But if you go through the plane of the galaxy, there is at least a class of quite high luminosity stars, so things that correspond to things that are 40, 50, 60 upwards, which are sometimes called luminous blue variables stars, although luminous blue variable stars are a very hard category to pin down exactly what people mean by that. But they're a class of high luminosity stars in the Milky Way, where surrounding them you see shells, usually at 24 microns. And if you infer the amount of mass in this thin shell, it can frequently be around the solar mass of material. If you play games with the number of those shells surrounding the stars, you can estimate a lifetime for those shells. And you can work out that this mode of eruptive mass loss may be as important for the mass loss of these high mass stars as any sort of wind. And so this could be an important or dominant form of mass loss for the highest mass stars, and of course mass loss controls much of how these stars evolve. And so another reason for worrying about these transients is they can be an important component of stellar evolution, which in fact are not included in any models of stellar evolution because, as I said, no one knows how this mechanism works or exactly how much mass comes out. So that's sort of the context. So let me just remind you of this object. First, everyone should see pictures of Eta Carinae. It's pretty. So somewhere around in the 1840s or 1850s, this star, which was already fairly bright and seen by eye, suddenly became quite a bit brighter. And I'll show you a light curve in a little bit later. And this is what it looks like today. And so it's probably, at birth, was over 100 solar masses. In this eruption, it ejected something like 10 solar masses of material. This material formed dust and now forms this dumbbell-shaped nebula here, which is known as the homunculus, because in old photographic plates it looked like a little man. And this dusty material here absorbs 90% of the emission from this star and re-radiates it in the mid-infrared. So I'll show you a number of these spectral energy distributions. So they're all log wavelengths, and then it's nu L nu, so energy per decade of luminosity. And so it's amount of energy. Here's the SED of Eta Carinae, the points, and 90% of the emission is coming out in a peak around 24 microns, and that all corresponds to emission by dust out in this shell. And it's simply because this shell is now fairly large, the dust temperature you get is fairly cold, and that's why it's at 24 microns. If you want a little bit of fun, there's actually, you see the optical light coming through there. Basically, absolutely none of that is direct emission from the star. All of that is light scattered off of the dust as well.
What's the physical scale?
It is 10 to the 16 to 10 to the 17 centimeters at this point. Somewhere around there. Okay, so here's the light curve. The Mark I eyeball was pretty good at doing this. Mark I eyeball is good at something like a third of a magnitude or so, if you have good comparison stars. So here's the great eruption. It was around third or fourth magnitude before the eruption pops up. Sort of in a decade, fades. A little bit in the 1890s, it popped up again. Then went dead flat. And then sort of starting around the 1950s, it started to recover. Okay, and so right now it's been steadily getting brighter in the optical. And what should happen in the course of the next 20 or 30 years is basically the star will emerge and the infrared radiation will start to collapse as the surrounding dust becomes optically thick. So what would you expect if I take a star, and the picture of this is in whatever, the 1850s. This star ejected 10 solar masses of material, and that material heads outwards. Okay? Dust forms basically as a collisional process. So dust grows when the density is highest, and as the density drops, the growth of the dust particle shuts off very quickly. And so you just sort of ask is, suppose I turn on, I'll just picture it as a wind that's going to last for a while. I turn on a wind at some point, and I turn off the wind at some other point, and I ask how the optical depth associated with that wind works. And we're just going to assume this, you get to some radius where dust can form, the dust forms immediately, and then it's just drifting outwards smoothly. If you take that sort of geometry, the optical depth of that shell basically just scales as 1 over the inner radius minus 1 over the outer radius. And so if you just track, if you know how much material is in the shell, and you're assuming that the opacity of the material in the shell is not changing, okay, then all you have to track to see the evolution of the optical depth through that shell is to keep track of where the inner and outer radius is, and it's basically just a ballistic track. You've ejected the material, it's going to move out at basically a constant velocity. What's the inner radius? Well, in order for the dust grains to form at all, it needs to be cool enough that essentially the dust grains don't evaporate any faster than you assemble them. And that's sort of the temperatures of around 1500 Kelvin. It depends on exactly what composition you want. And so that's just some radius where the dust temperature will be that low. If I initially start with a wind, when I first start making dust past that radius, well, I don't have much dust there. And so initially I don't have much opacity, and then it builds up as I have more and more material from the wind has gone past that formation radius. In the limit that I kept doing this forever, it would turn into the optical depth of an infinite wind. And so for an infinite wind, right, that becomes infinity, and the optical depth just depends on where the inner edge is. Okay. If I then turn off the dense material forming dust, so I might just quickly drop the density to the point where I form negligible amounts of dust, the absorption associated with the shell initially drops very, very quickly, right? Because if I imagine this is now big, then the optical depth is basically dominated by what this number is. And so the time for the optical depth to drop by a factor of 2 is just the time for the material to move from wherever the dust was forming to twice that formation radius, which is a fairly fast time scale. Okay? And so here's the dust rising. Okay? Here's it's trying to go flat to being a steady wind. When I initially turn it off, it drops very, very rapidly. And then these are sort of details of how you turn it on and off. And then eventually what you have is essentially you just have a shell of material, and the optical depth just depends on the surface density of the shell. And so at late times, the optical depth is just dropping as 1 over time squared as the shell expands. You can put many elaborations on this. Most of the elaborations will work to accelerate this evolution. So for example, most shells of material, as you eject them, evolve from smooth to patchy. And as you evolve a smooth shell to patchy shell, you would have this optical depth change more rapidly, or the average optical depth change more rapidly. It's very hard to come up with anything which would make this evolution of the optical depth slower than this prediction, this simple, just spherical prediction. The curious thing is no example of an imposter, or actually Eta Carina itself, actually shows this behavior. So the picture in these things is the imposter goes off, ejects some material, and people say, okay, it's an imposter. And in some cases, they then go back and go looking for the star which did this, and in several cases, they think they can find it. The star they find as the survivor is always some 2 or 3 magnitudes fainter than the progenitor star. And this is interpreted as being due to dust absorption, which would certainly be true. Eta Carina would have been heavily absorbed for a period and would be fainter than its parent star. The problem is that if you go and look, none of these things seem to be mid-infrared sources, and none of them show the optical brightening you would expect from sitting behind a veil of dust that is steadily getting thinner as it expands outwards. So something is odd about this picture. And we don't know what the solution is, but let me show you one example. So here are 3 examples. These two guys are prototypical or archetypal extragalactic imposters. The phone numbers don't matter. This one is actually a normal luminous blue variable star. It varied, it triggered a supernova search just because it was already sort of a million solar luminosity star. It fluctuated upwards and it was so bright that it triggered the supernova search. So then what we do is we look at these things with difference imaging, right? The LBT for these distant galaxies, you can't do photometry of individual stars very easily. But what you can do is you build a reference image. That's what's shown here at a not marvelous stretch. And then for each piece of data, you subtract that reference image to look at the changes. And then you can play games. And this is the other two images are a little game. As I have a time sequence of these images, and I can fit that time sequence of images pixel by pixel as a line. And so I can ask at each pixel, what is d luminosity d time? So I'm basically making a slope, temporal slope of the brightness of this galaxy. And then I can look at the residuals from modeling the temporal variations of the slope. So here's the slope of the brightness, and here are the RMS residuals from making the changes in brightness at that pixel linear. The scale here is that saturating the color on the slope is something like 1,500 solar luminosities per year. Okay? And this guy is just a varying bright star. It went up in brightness and has now been fading back in brightness. It has a big negative slope, and it's got some curvature, so it's not perfectly fit. Okay? Here are the two imposters. Okay? The things that were found as surviving stars were a factor of 10 or so fainter than the stars were before the transient. Okay? You explain this by when they were first rediscovered, which was now some 10 years ago, putting a shell of dust around them to produce a factor of 10 absorption in the optical. Okay? Now you've had a certain amount of extra time for that shell to expand, and I should be seeing that drop in optical depth. Okay?
Why is the optical brightening the symptom rather than the ratio of thermal infrared to optical? It's a diagnostic of what the mean optical depth is. Because I don't know what the eruption has done to the underlying brightness.
This is a somewhat tricky point. So you could take a different view. This is not the standard view, so this would be another way of interpreting it. Is that basically after the eruption, the star is kind of tuckered out. And so while it's tuckered out, it's going to remain subluminous. So in the end, that would be an escape, but that is not the normal view of what people have. What I'm describing is the normal view, and it doesn't degrade, so that would be another solution than what I'll be talking about. But basically, you can go through the numbers, and basically for the thinning of the shells you would see from this dust hypothesis, there should have been blips here, or maybe a blip here, but there just isn't. And the same is true as if you go to Spitzer and look for the emission from the dust. You don't see it. So something about this picture for the normal imposters is wrong. In fact, for Eta Carina, it's also wrong. These curves here are curves as this is what you would expect for the brightness of the star. If I normalize it recently, where the optical depth is about 2 in the visual, and run it backwards as t squared, right? That should have been the magnitude of the star. So if I go back to 1880, the actual magnitude of the star should have been about 20th, okay, just from running the dust we see today backwards. Whereas in fact it sat there at about 8th. Okay. You can try to make the shell patchy, so this is a game for trying to make the shell patchy. You can sort of suppress the evolution, where basically what's happening is, as time passes, it is easier and easier for the light to leak through holes in the shell. And that lets you suppress the evolution, and you get that, it should have only been, whatever, 18th magnitude in 1880. The curious thing here is what this light curve really looks like is you turn on a dusty wind in the eruption and then you turn it off again around 1950. That's what this curve would do. It's just a crude, it's just a by eye. So if I turn on the dust here, let it run constant, again, a wind, if I run it, goes to a constant opacity, constant optical depth of opacity. And then when I turn it off, it recovers. And so the difference between these curves and that curve, there is nothing you can do to rectify the difference between those in this picture of just an expanding dust shell. If you think that what actually happened with Eta Carina is it went into a dense, dusty wind phase, then it's relatively easy to explain this light curve. You could also try to explain this as, let's just say this is a tuckered out phase. The problem is you're still stuck, right? Because you know that the optical depth here is 2, you know you're surrounded by a dusty shell. You still have the problem that you're trying to use a change in luminosity to fight, which is your linear in, to fight a change in the optical depth, which sits in an exponential. Right? It's very hard to fight something in an exponential with something which is not in an exponential. And so the tuckered out star makes it very hard to explain this. The counter to this is saying you want to make it a wind, which does not make this point popular with the Eta Carina aficionados, is that where you see proper motions of the surface of the dust, is the surface proper motions of the dust look more like that they all came out in the 1850s. I don't have any particular reconciliation for that. It's just that if I made a shell that dusty in the 1850s, okay, and try to run it backwards, I don't know how to reconcile it with the light curve I see. So I don't know what the solution is, but if I just want to explain this light curve, it's a lot simpler to do it as a wind rather than a short duration eruption.
Why do you assume that the shell is spectroscopic because Eta Carina is sitting on?
You can play games. You can actually show that making the geometry more complicated produces a standard form of an asymptotic integral. And as a result, you can show that the geometry doesn't matter very much.
No. Not completely because the light comes out.
Look, I'm not going to claim this is a complete solution, but it is true is that it's very hard. The problem is basically things like to evolve from homogeneous to inhomogeneous. Most of what you need to explain that is you need to have evolution from inhomogeneous to homogeneous. That's very weird. It's anti-entropic in some sense. And so I think that's what bothers me about any more complications of geometry. Is that implicit in many of them is you have to have an evolution from inhomogeneous to homogeneous rather than reverse. But you can make up those little differences by changes in luminosity and temperature. Those are now small enough that little fluctuations in the star can make up the difference. Okay? But when the difference is 10 magnitudes, there's nothing you can do to luminosity and temperature to make up the difference. So, and in fact, this would be the simplest way if you want to keep to this eruption model of keeping this classical imposter view. Is that what you want to do is rather than having the mass ejected during the optical transient, you want to make the optical transient a signal that the star has entered a high mass loss phase. And that the high mass loss phase continues for an extended period after the optical transient ends. And in that case, you can support a high optical depth in dust for a much longer period of time and explain why you don't see it. The implication, though, is that if you look hard enough, you should still see the mid-infrared emission. Okay? And if you went to a longer wavelength, like with HST and in the near IR, you should be able to punch through the dust and clearly see that you have an extincted star underneath. In practice, if I really wanted to, other than the question of energetics, you could make an equally good story for these objects that there is no surviving star. And it's just a misidentification. I'll give you one reason to worry is the identifications for the surviving stars always have the only magnitude a surviving star could have and be called an identification, just from the values of the data. If you look at the data, put down a circle, and said, what could I possibly identify it was, if you did it wrongly, you would get something of the same brightness. Right? It's just, if you look hard enough, you put down a circle, there will be some star of some brightness, and if you make a misidentification, it will be right about the limit of what you can detect, and that's what all these things are. Okay. So that would be the counter. And the problem basically is people look at these things and then stop looking at them. So this is a soluble problem if you look at them again with Hubble or something. It's just that no one's really done it. Okay, so that's the one class. These things are like 25 solar mass stars. The imposters you've got here, where you have information about the luminosity of the objects, they are not million solar luminosity stars like Eta Carina and the luminous blue variables. The luminous blue variables are generally believed to be stars which are above 50 solar masses. These extragalactic imposters are actually all stars around 25 solar masses. So whatever they are already different stars from what Eta Carina is. So this gets to the second class of object we had, which, to annoy Jose Prieto, who first found it, we call internally Prieto objects. And then he cringes, which makes it fun. So in 2008, there was a transient which was identified as supernova 2008S in NGC 6946, the fireworks galaxy. It is our local record holder. It has had 9 assigned supernovas since 1900. It beats the next galaxy out by, I think, a factor of 3 in terms of number of supernovae. And it was fainter than normal supernova. It showed these type 2n spectra. And this was sort of shortly after the LBCs were commissioned, and it happens that we had some images of NGC 6946, and they were plenty deep enough to go and find it, and so Jose went looking for them, and it wasn't there. And then he had the bright idea, I think not for the reason that will turn out that it was a bright idea, but I think he was just thinking is, well, how can I hide it? It could be behind dust, just in a dust lane. And so maybe if I go to Spitzer, I could see, Spitzer's 2 mass wouldn't be deep enough. Maybe in Spitzer I could see through the dust and see that there was a star behind a dust lane there. And so in fact he did find a star in the Spitzer data. And so here's the V-band LBT image. Laser is, okay. You should easily have seen something there if it was a star that could become a supernova or a community. It's not really there at 3.6 microns. And then it comes up as a source at 4, 5, 8 microns, and then you don't see it at MIPS, but the sensitivity is down. There's no ambiguity about the identification. Is the probability of you're putting down a 1 arcsecond circle on one of these galaxies and circling a red mid-infrared source is basically 0. There's no real risk of confusion in addition to any other problem. Then the second example occurred only a few months later in a southern galaxy, NGC 300. And here's what their spectral energy distributions look like for the progenitor stars. And so here are the LBT limits. Okay? And then here's the Spitzer SED. Okay, so down at 3.6, comes up here, then the limit at 24 microns. The NGC 300 one happened in one of Julian Del Canton's HST stellar population survey fields. And so you get spectacularly better optical limits. And so here are the optical limits on this one. And then here it comes booming up in the mid-infrared again. Okay? So both of these progenitors, whatever these transients were, had luminosities of about 30,000 solar luminosities, and apparent photospheric temperatures about that of boiling water. Nominal, if you think of them as a black body, they have nominal temperatures of 400 Kelvin. The most probable explanation for what these are, and I'll show you some other evidence why this is a good thing, is that these are a form of extreme AGB star. And so if you get to the star sort of around 8 solar masses at some phases when they're on the AGB branch, they can have incredibly dense and slow-moving winds, so up to sort of 10 to the minus 4 solar masses per year. If you take something around 10 to the minus 4.5 solar masses per year, run it slowly the way the AGB winds go, you can produce a mid-infrared photosphere out around 10 to 15 centimeters, where these things seem to have their photospheres in order to show this low temperature. The implied visual optical depth outside that is something like 100. Right? So the ratio of sort of the mid-infrared out where we're seeing this opacities to the visual opacities is around a factor of 100. So outside the mid-infrared photosphere, you have to have an optical depth of order unity, and so the optical depth outside of that has to be roughly 100 times bigger. So you combine this property of the winds and the luminosities, and you would say this is probably something like an 8 solar mass star, so much less massive than what I call the classical impulses. The other reason to think they're AGB stars is you can go and look at where they sit on a color magnitude diagram. You have to look at a mid-infrared color magnitude diagram because, of course, you can't put them on an optical color magnitude diagram. But here's a color magnitude diagram of M33. And so here are the normal stars, which in Vega colors for Spitzer's 3.6 and 4.5 micron bands sit at 0. This coming off here is the AGB sequence. Okay? And these guys sit way over here. Okay? Extremely red compared to almost any other stars in these galaxies. Typically, we sort of analyzed up to, I think we did, in the end, did 7 galaxies. A typical galaxy has, depending on how you want to count it, 1 to 10 stars with properties similar to these guys. So they're stars with extremely rare mid-infrared properties. These other objects are sort of various known other objects. So here's Eta Carina. NML SIG and VYCMA are other forms of dusty red supergiants. These circles, the squares here, or the triangles here, are mostly candidates for luminous blue variable stars, which is sort of what Eta Car should be if it didn't have quite so is, but is surrounded by more dust. So the luminous blue variables generally sit along here in a sort of very different spot for where these guys sit. Their rarity is such that you can sort of ask what their lifetime in this phase would be, and their lifetime in this highly obscured phase can only be something like 10 to the 40 years. So it's rare, and that implies it has to be short-lived. And at least some of them, when they get to the end of it, do something. The next thing we can worry about is what kind of transient they were. As I said, the picture of most of these imposters is that it's some sort of radiatively driven process. Is that somehow you drive a portion of the atmosphere of the star to be super Eddington, and then that super Eddington then leads to a driven mass loss process. These guys, there's a pretty good argument that they have to have been explosive. And the reason is that you saw them. Remember what I said, is the progenitor star had an optical depth outside the infrared photosphere of something like 100 in the visual. But they were found by an amateur in the optical. In fact, the absorption at the peak of the transient was an optical depth of something like 1, not 100. So something in this had to destroy all of the dust. Well, how do you destroy dust? Well, it's sort of the inverse of having to get to a temperature where you can make the dust. If you can heat the dust back up to around 1500 Kelvin, again, it depends on the composition and the exact grains, then the dust basically can evaporate and you can destroy it again. And so you can ask, well, I saw this transient, I know how bright it was at peak, and I can ask how far out did it have any capability of destroying the dust? And the answer was that the observed transient couldn't come anywhere near to making this thing visible in the optical. That if we had depended on the observed luminosity of these transients, the optical depth at peak, even if I'm wildly generous, would have remained several tens. And this amateur would never have found it unless he has some really bizarro equipment where he's doing 24 micron observations on a 10 centimeter telescope from, where is it? I think he's from South Africa. If you ask how much luminosity you need, so the observed peak was something like 10 to the 8 solar luminosities, so about an order of magnitude less than a supernova, a normal supernova. To destroy all that dust, you need something like 10 to the 10 solar luminosities. You don't need it for very long, and in normal supernova, the interpretation of this is what's called a shock breakout. So if you imagine a shock going out through the envelope of a star, as it goes through, it's moving at a quite high speed, and so it heats things to its characteristic temperature. So these shocks, at least if we take the velocities you see in the spectra, the shock was moving at something like 1,000 kilometers per second when it came out. And so basically, as the shock went through the envelope of the star, it was heating everything up to temperatures of order keV. Okay? But of course, you don't really see anything initially, as the shock is heating everything up behind it to that temperature. But as long as the shock is very deep in the star, okay, the time scale for the radiation to diffuse forward towards the surface is slower than the rate at which the shock is advancing. And so as long as that is true, as long as the radiation diffusion time is long compared to the shock speed, okay, the radiation stays behind the shock, except there's a surface. And so right when you reach the surface of the star, and there's a particular definition of that, it's when you reach an optical depth, which is the speed of light divided by the shock speed. The time scale for the radiation to diffuse out of that layer now becomes shorter than the time scale for the shock to propagate. And essentially what happens is that last layer of radiation associated with the shock going through the surface of the star gets sort of valved out and escapes very quickly. Okay, and that's what the shock breakout luminosity is. It's the radiation associated right with the skin of the star as the shock breaks out, can escape very quickly, and you get a very short, brief spike of radiation coming out. And this is predicted to occur for normal supernova, and in fact is explained or used to destroy dust around normal supernova. It's very hard to see because its duration is the light crossing time across the star, essentially. So even for a red supergiant, you would get a pulse comparable to this, a normal supernova on a red supergiant, you get a pulse comparable to this, but it lasts only half an hour. And so it's just very hard to see. There are a couple cases where people think they may have seen it.
Does it also mean sort of that the optical depth would drop within an hour? That is, if you were looking at the right time, what would you see within that hour?
Worrying about the dust or no dust?
Worrying about the dust.
Okay, so with no dust, all that happens, right, it then drops again because the rest of the radiation is deeper in the star, and so the other radiation further in the star still has a longer diffusion time. Okay? With the dust, you would have the time scale for that radiation to destroy it, and at these luminosities, the destruction, you don't really, if you have a half an hour, that is plenty to destroy the dust, at least in these normal theories. So it counts as more the peak luminosity than the duration. And you could make it short enough that you would just ablate the grains. And it's something like, I think the number came out is, the number I quoted out is the point where you would destroy sort of 50% of the opacity was the estimate I was using for where you destroy the dust.
And the infrared luminosity very briefly goes up and then drops? Is that
Yeah, so you would get an infrared echo off of this, briefly. But in order to do do this, right, you actually have to have an explosion. Right? No explosion, no shock, no extra peak. If I'm just driving this by suddenly doing something to the opacity to increase the luminosity to 10 to the 8 as part of driving this mass loss process, I don't get anything like this. So there are theories for this, going through all the details of how this radiation gets out. And for these sort of parameters you get, it turns out as a nice coincidence that if you ask how big a star you need to have in order for the luminosity to be high enough to destroy the dust, you get that the star had to be a red supergiant. You don't get a great estimate of the temperature of it. It's a big star, even for a red supergiant, which again favors this idea that the progenitor is probably a super HEV star. All right, what happens next? Well, so at peak, as I said, the optical depth wasn't high at peak. And so because 6946 has had an infinite number of supernovae, there are an infinite number of Spitzer observations of it. And so this guy happened to sit in a field where people were monitoring the evolution of another supernova. And so they actually got an epoch of their data shortly after the transient. And so here it is there. It's faded a little, and optical it peaks at 10 to the 7, and then you can see this big infrared tail on it. And then just watch what happens as it evolves. The optical goes away, the infrared stays sort of constant, and it keeps going, and it keeps going, and so here it is after 3 years. It's completely gone in the optical and even near infrared. I'll show you, we can barely find it in the near infrared. And then it comes zipping up again in the mid-infrared, and if you remember, its total luminosity before explosion was about 30,000. And so you can see it's still sort of order of magnitude brighter than the progenitor star 3 years after the explosion. So here's just an example. Here's how it looked in late 2010. So here's the Spitzer. If you can remember in your mind what it looked like before it exploded, okay, you could barely squint and see it. Now you don't have to squint. Here is a 3/4 of an orbit of HST at H-band. You can all immediately see the star, which is the survivor. Okay. In fact, all you're seeing is a sea of rather garden variety red giants with luminosities of hundreds or 1,000 in the H-band, solar luminosities in H-band. In this case, we're pretty sure we know exactly which star it is because we actually got 2 epochs. And so there it is in 2011. 2010 August, a year later, it faded, and if you do difference imaging, sort of right in the crosshairs, there's an object which faded, and so we're pretty sure that's the object. But if you don't want to trust us, the thing is 100,000 solar luminosities in the mid-infrared, and it's under 1,000 solar luminosities in the near-infrared. And so this thing is still completely blacked out again. So the simplest way of trying to explain this seems to be is that this is not dust formed in the actual ejected material. It turns out that the pattern of how those SEVs change are not consistent with putting the dust at that radius where the shock would be, so material ejected. It can't be material from, say, a reforming wind around the star. That would be even closer to the star. In fact, a reforming wind around the star would be too close to the star to even form dust at this point. And so the only alternative you're left with is, well, I started with this very dense, dusty wind. I destroyed most of the dust, but of course I didn't destroy the material. Okay? It cools off, it recombines fairly quickly. But if you go through the rates at which, and you have to sort of gloss over how the nucleation works. My wife, who works on nucleation, says I'm allowed to do that. So I can't question that. But then basically you're limited by your ability to regrow the grains just by collisions. And so you can work through the collisional growth rates, and you can find that the densities of these winds are actually high enough that if you say anything nucleates, the grains can actually grow and produce a substantial optical depth again, after the explosion in the wind. And so the picture is sort of this. So here's time, here's some measure of radius, and if you watch where, say, that the dust would be heated to something like 1500 Kelvin, you can't have any dust inside this radius, okay, for the transient you see. Remember, the mid-infrared photosphere originally was sort of out here, so the peak of the transient could barely destroy dust to the mid-infrared photosphere, but of course you have to have material outside the photosphere as well. You should not have old material inside the shock, so here's the shock going out, so as the shock goes out, it would re-destroy any dust in here. Okay? And then you can sort of ask, is there sort of this regime in here where you can regrow grains? And it's not a world's best quantitative model, but qualitatively, you find that the rates and your ability to regenerate the opacity kind of works. And so, modulo a better hypothesis, this seems to be what happened. The other clue is what you see is if you watch that SED and you ask where is the dust that is producing the infrared radiation, it actually starts at large radius here. And then if you ask what radius it wants to be in, it moves inward, which would be the pattern of dust reformation, because it forms wherever it is dense enough to form given the temperature. And so as the luminosity drops, you can form dust closer in, and so that's what it does. And then the radius where you seem to see the dust starts to go out right about where you think the shock would start to reach that dust radius. So at least it sort of holds together. If you ask what's the luminosity today, the simplest explanation within this story is, well, I had a shock. The shock came out of the surface of the star, and it didn't suddenly say, okay, I'm done. It keeps going through the wind. And if you ask what luminosity you get from a 1,000-kilometer per shock going through a wind of this kind, it basically produces about 1 million solar luminosities by re-shock heating the wind, or shock heating the wind. And that would be a simple way to maintain the late time light curve by basically reprocessing a lot of this. And you can say, well, wait a minute, usually you don't absorb X-rays. Except, remember, first of all, this is a dense wind, and secondly, this is not a very energetic shock. So it has a temperature of only a keV, so they're pretty soft X-rays. And soft X-ray opacities are pretty much the same as dust opacities. Okay? And so if you have enough material that would support high optical depth in dust, you have enough gas and atoms that will support high optical depth in soft X-rays. For the X-rays, it doesn't matter whether dust is there or not. It's just how many atoms are there with enough electrons attached to them. And so a simple explanation for why it's still 10 times brighter than progenitor is the shock is going out, it's producing soft X-rays, the soft X-rays are absorbed on the gas, that produces some cascade of UV, optical, etc. line emission, that's then absorbed on the dust, and then that's what you see on the mid-infrared emission. We did use Swift to search from X-rays from a number of members of the class, and we got an upper limit, but not tight enough to sort of rule this picture out. We have Chandra observations of another, and we just haven't dealt with them yet. But the prediction of this holds together is eventually you have to see down to the shock, and you should eventually emerge and see a line spectrum from the shock, and you should be able to see the X-rays coming out eventually. And if you don't, well, I wrote this paper with my theorist hat on, so it was a good idea. If it's wrong, fine. Okay, I already said that. So are these things supernovae? An interesting coincidence about this is that this mass range around 8 solar masses is also exactly where a particular type of supernova is predicted. They're called electron capture supernovae. And so these are stars where you form an oxygen-neon magnesium core, and basically it undergoes core collapse without ever making iron. It's basically the same process that eventually the electrons capture onto the nucleus as you approach the Chandrasekhar limit. You lose the pressure support, and the thing collapses, but there's no iron. These are predicted to be much less energetic than normal supernova, which is at least consistent with these things. Whether the energetics actually match or not, some people think they do, some people think they don't. But in the final analysis, it does seem to have to be an explosive transient. If you play with the energetics somewhat more, and play with what you see a little more, you get that it probably had to have thrown out something like a solar mass of material in order to make these things work. The total radiated energy is not that dissimilar from things that are believed to be low luminosity supernovae. But there's no proof until you can find that the star is actually gone. Unfortunately, there are other members of this class where you can still see the infrared radiation 10 years afterwards. So it may be a bit of a test of patience to find out what these things ultimately are in the end. We don't know how bright these guys were before they exploded, because no one knew to look for them. Perhaps they were just more distant. But if you sort of watch what's happening, so here are the two I've talked about. They're sort of fading at 3.6 and 4.5 down to 10,000 solar luminosities. That's probably mainly an effect of temperature more than of total luminosity, right? Because 3 microns and 4 microns, as time passes, correspond to dust that's fairly hot compared to how far out you have to be. And then some of these other guys are still at that limit 10 years after peak. And so the only real solution is you have to be able to find and characterize basically the evolution of the dust and the optical depth down to any surviving star. And so patience will tell what's happening. All of these are actually invisible in the near infrared. In fact, except for 2008S, where we had 2 epochs and could see the changes, there you go. Pick which one you want to be the star. Those things up there are about 1,500 solar luminosities in H-band. So the limit on the H-band luminosity of that star is 300 or 400 solar luminosities. So whatever's happening, these things are heavily absorbed again, whatever mechanism you want. And then you can look at the environments around them, and with one exception, if you look at the stars and the surroundings, if you look around that guy, right, there are no high luminosity stars. And so these things basically look like they have environments which correspond to the massive stars being in the environments of around 10 solar masses, which is again consistent with these things being relatively low mass stars for this relative supernova. Okay, so that's what we ended up with. That we have this assortment of imposters. And if we look more closely, we've unfortunately ended up with 3 classes of things. We should call them probably class 2, C, and F. And then that would give us a higher probability of it being right than if we called them A, B, and C in the end. But there's some are just massive stars that trigger supernova searches. It's just a massive star, it fluctuates bright enough that Alex's company says, gee, look, we should look at this more closely. But there's no sign of dust formation, and it just sort of fluctuates along. This guy's been known to be a luminous blue variable for 50 years. There are these classical ones, which seem to be roughly 25 solar mass stars, where the simplest explanation, if you want the surviving star to be, is to put these things into a high mass loss phase after the transient and just use an ongoing wind to hide the objects. Or you could go for the tuckered star hypothesis. And I sort of rejected that so far just because it doesn't make any sense for Eta Carina. It doesn't solve the problem for Eta Carina, so I didn't really want to invoke it to solve the problem here. And then there are these heavily obscured super AGB stars, which seem to have to be explosions. So there's nothing requiring these to be explosive, as far as we can tell. These guys do seem to have to be explosive. Maybe they're electron capture supernova, maybe not. The only way to find out is to keep watching them. None of them, however, are analogs of Eta Carina. None of them look anything at all, behave anything at all like Eta Carina. The only analog we sort of knew of Eta Carina before was Eta Carina was Wiki's prototype of the Type 5 supernova. You all aware of the Type 5 supernova? Okay. It had 2 members of the class. One was Eta Carina. I think we know Eta Carina was not actually a supernova. And the other one was this guy, supernova 1961V. Which is quite a spectacular star. It had been monitored with photographic plates. But it's an 18th magnitude star at a distance of 10 megaparsecs. Okay? So that's quite a star. It's several billion solar luminosities. And, well, empirically, here's before, here's after. Okay? Well, that looks good for calling it a supernova. But of course, if we did this with Eta Carina, it would also probably have vanished in this case, because you do get a significant optic depth. The problem is now we can go with Spitzer. We sort of joke that if you've seen the Spitzer picture of the catalog of pretty pictures of galaxies, is that if you take Eta Carina at this sort of younger age of tens of years to 50 years, you could spot it on that poster from across the room. Right? This would be a booming mid-infrared source. And so you can go and look at the archival Spitzer data. Here's this spectral energy distribution of Eta Carina. A nebula around 61V should be about this luminous, and then it should be a little bit hotter because it's younger. Okay, so it would shift to bluer wavelengths and so on. And if you look at the region which should be most associated with this, here's kind of the limits on the infrared emission. And there's no way of splitting up the 24 micron band. It's still an order of magnitude below. And so basically from the optical through the mid-infrared, there is just nothing there with anything close to the luminosity of a million solar mass star. And so our conclusion was there's no surviving star here. And the other point which Nathan Smith has made more is that, in fact, the energetics of this guy are, this thing did not have the energetics of an imposter. Even in the optical, it had the luminosity and energetics of a normal supernova. It just had a peculiar light curve, which today would be much more accepted because there's now this class of what are called hyperluminous type 2n supernova. So not only are the faintest supernova type 2n, but the brightest supernova are also type 2n. Because the 2n, all the 2n really says is you have a surrounding circumstellar medium for the shock to interact with. And the very brightest supernova are also 2n because you make them bright by having those interactions. And so this one looks more like the nearest example of one of this other type of 2n than one of these imposters. So let me say a few words. Let's just ask, are there actually any Eta Carinas? You can't really look in the galaxy. Right? The lifetime is clearly, there's only been one such eruption in the last 200 years. There's one of P Cygni if you go back another 200 years. But if you want to look for the eruptions or even do a counting of them, it's hard to do it in the galaxy just because they're rare. You don't know distances, it's hard to do completeness, you don't want to count anything in a galaxy. But Eta Carinae, as I said, is so bright we can go looking for it in other galaxies in the archival Spitzer data. It's not ideal. You really want to do this with James Webb at 24 microns. There are lots of things I want to do with James Webb at 24 microns, but at the moment I have Spitzer at 3 and 4 microns. I have to do it with a little shorter wavelength bands to keep the angular resolution up. And what you're basically looking for is things with high luminosities that rise up like this. Okay? And so you can do this for nearby galaxies. And it's basically you've raised the luminosity threshold so high that your problems of confusion start to go away. And it turns out the main source of contamination, which is convenient given some of my other hats, is AGN. And so if you count the number of AGN you should find in the survey fields, given the same selection criteria we use, the sample should be dominated by AGN. And so I won't show that. So we found in 7 galaxies 46 candidates. If you do the statistics for the numbers of AGN, you get that almost all of those should be AGN. In fact, a number of them already are. And so we expect something like 6 candidates to survive after subtracting out all the AGN. If we go through that and find a number in that category, you would get that the rate of actual Eta Carinae eruptions is something like 10% of the supernova rate. But we're only partway through that. So as I said, the only way you can reach a conclusion on what's happening with these transients is you don't learn anything from the optical transient peak. The optical transient peak tells you almost nothing about these things. The only way to really figure out what's going on is to follow them as what's happening at late times, because the evolution in the optical depths you see, the evolution in the temperatures you see, is what will tell you the actual energetics, the actual amount of mass ejected in these things, and that will give you a much better probe of the mechanisms. And it may be frustrating, slow, but in the final analysis, if you want to just worry about the supernova or not supernova question, in the end, either there's a star or there isn't a star. And so at least that's a sort of fairly simple binary choice. But as I said back at the beginning, there are sort of interesting questions associated with these objects, in the sense they may be an important part of stellar mass loss, high mass stellar mass loss, that's simply not included in models. And the first step to figuring that out is, for example, to figure out exactly how much mass is being ejected. And one of the best ways of probing that is to look at the evolution of the optical depth in these ejection scenarios. And as I said, the right way to do all of this is with James Webb. And as my colleague Todd Thompson wrote in the famous graduate student paper, which is called Slacking into the Future. I don't know if that sounds in the exact title, but it's basically a paper on when you should or should not do work. And this is for computation. You reach a point where for a particular class of problems, you should just go to the beach. You'd be much better off just going to the beach, coming back in a few years and doing the problem because the computers have gotten better. And this was written by one of the co-authors as a cat. This gives you a sense of the paper. And the problem here is the right way to do this is with James Webb, but I do have to earn my salary in the interim, so even though I would rather do it with Webb, we've been trying to do it with Spitzer. I'll stop there.
So do we have any questions?
You talked a lot about the dust, but you also would like to have kinematic information to reconstruct velocity fields, for instance. Why not just use molecular line observations? Which are very deep, and then you also get mass loss from molecular lines.
Maybe with ALMA you can do it.
I think you should be able to do that.
Certainly before ALMA you couldn't do it. Maybe we'll try. I should say, the basic kinematics, you have the spectra at, the optical spectra at peak. So you have a sense of the velocities to start with. But yeah, no, I take
for AGB stores, this exercise has been done to test in a way, and with that for AGB stores.
Right. Yeah, so the question would be, are there any slow-moving features left in the surrounding ejector? No,
You mentioned that they're important in the dust production. Did you mean because that may affect cell evolution in a way that hasn't been incorporated, or do you think they also have a chance of being actually globally important in the total amount of dust that's being produced in like galaxies nowadays?
So if you made every massive star do an Eta Carinae and produce dust, it comes out as not a major factor. In some sense, if suppose it was 10% of the supernova rate, right? and then it's less mass than you would expect from a supernova. It's the outer layer, so it's actually less metals. And so to the extent that supernovae are presently probably not dominant producing dust, these guys can't be. So it's mainly just as, in the case of Eta Carina, if you want to understand the evolution of Eta Carina and you say, I'll just put a normal stellar wind on it, well, clearly you have its mass loss history wrong. And that mass loss history does govern. Right? There are these various questions about, how do I get to a Wolf-Rayet star, and are the winds I see sufficient to get me from a star with an envelope to a Wolf-Rayet star? And then we can go and we can have a long discussion about clumping factors and so forth. But whatever it is empirically, Eta Carina and a bunch of other galactic stars where you can see this mass loss, you will clearly have the mass loss wrong if you don't include this mechanism.
So what I should have asked is, do we have any students or postdocs who want any
Necessarily.
Students will Thomas and Hans Walter, of course, qualify exactly. Then I'll give it to the student case. Hold on, first, sir.
You're talking about the star Eta Carina, but isn't it a neutral star?
Yes, the companion is significantly less massive. It's believed to be more like 30-ish, 40-ish solar masses. There are arguments about, some people would like to make the eruption driven by a binary interaction. Those don't seem terribly convincing to me, but there are people who believe it.
But the wind structure, both stars produce wind, so it's more complicated than just this simple spherical.
So it should certainly sculpt the shape of the wind. But the binary per se, there's no sensible binary interaction, right, given that it is not you're ejecting 10 solar masses of material. If I'm doing this in a binary interaction with a 30 solar mass star, 40 solar mass star, how long would the orbit of that star last if it was driving 10 solar masses of material to ejection? So the energy for doing the ejection can't be coming out of the orbit, at least not in a sort of sensible way. And then there are long, the literature on Eta Carina is extensive. But there are long debates about this and whether there are correlations between what you see, exactly what you see in the period of this binary. And Nathan Smith has shown pretty convincingly that most of the eruption events are not triggered with paracentric passages, for example.
So you mentioned at least the exomasses, that it could be shocks, X-rays, and heating risk.
Right.
But this should link to both, in the first stage, you have the optical diagnostics, but in the dust obscure stage, you might have really direct line diagnostics.
Right. Yeah. So if you could look for the narrow mid-infrared lines, you would see some from the shock there. It's hard to predict because the people who have done these shock models have not run them in this regime. Point me towards them. But at least for the ones you've got, it would be tricky to see it given IRS sensitivities. We did get an IRS spectrum of OADAS, and there weren't any line features. It was pretty clearly graphitic dust. In fact, Chris Shelgren said it looked sort of most like what you would sort of see in protoplanetary nebulae, which is sort of, again, sort of consistent with this sort of AGB. But yeah, so if you could do good mid-infrared line spectroscopy, those should just get through. Yes, that would also. But again, I'm not going to the beach.
Any other questions?